Thanks everybody for joining and welcome to our session. So today we're going to talk about basically how we can leverage advanced accelerated networking to reach the sustainability, performance, and scalability goals, actually to build AI clouds with some real life example, which my co-speakers will share about. And basically, first I wanted to kick it off basically to speak about how NVIDIA networking solutions can enable AI clouds. And basically, I want to emphasize the importance of the accelerated networking to scale and improve performance of the modern AI infrastructure by offloading and securing the data center intensive applications such as AI. So the networking and specifically our solutions can reduce latency, can improve performance, and in general optimize the AI applications, which is really important when you build not just kind of a single user AI deployment, but you build a cloud where basically the multiple consumer need to get access and connect and use the AI applications from the cloud. So let me start from a very high level overview of NVIDIA AI stack. Which is powered by our accelerated networking, and this is a kind of the baseline of kind of the backbone of the AI cloud that we are promoting basically our customers to build. So on the top level of the NVIDIA AI stack, we have blueprints which guide and speed up the deployment of entire AI solutions, and these are backed up by the NVIDIA NIMs or inference microservices. That are essential pieces basically to quickly and easily deploy individual AI models across any type of the data centers and cloud. And on the lowest level, we have NVIDIA frameworks, which actually specific frameworks and SDKs enabling specific use case and in specific AI domain, such as telco, healthcare, automotive, and many others. So all that is NVIDIA AI stack. And all these layers are actually benefiting from accelerated networking to make sure that they can deliver the best performance, scale, and efficient scale, and basically security. So for that, acceleration is really crucial for AI cloud deployments. And if you look on the kind of base layer of enabling all this AI stack, so in the cloud, it's essential to have the set of accelerated services, specifically for cloud deployments, such as like SDN service, which can accelerate the networking and enable multi-tenant VPC to host multiple users in the cloud, load balancing to enable cloud-native application and traffic management for basically extensive application demanding to the traffic. The firewalling, which can secure the users in the cloud and then provide the cluster firewall service for AI cloud applications. NIM security specific framework, which can secure and enforce the security on AI workload running on in the cloud, basically for malware protection and basically antivirusing. And the storage, which is a very important part of the AI because AI demands a lot of data and it's very critical to provide really high performance access to the storage. So all these services need to be backed up with some acceleration, and for that we have NVIDIA Docker, which is enabling the layer across NVIDIA AI networking to basically as a framework to deliver an ability for all these use cases to be accelerated with NVIDIA networking devices and such as BlueField DPUs and Connectix adapters. And basically, in short, all these services need to be accelerated, and this is very critical in AI cloud. So compared to compute-only cloud, AI applications demand kind of very excessive requirements to performance, to security, to sustainability. So where basically our NVIDIA AI networking and Docker can help. Now a couple of more words about Docker. So probably heard a lot of stuff about it on other sessions, but just a recap. So Docker is our software framework to enable accelerated networking applications on the host across all the portfolio of our BlueField DPUs, connected NICs and super NICs, basically to leverage the best performance and scale for data center applications. So Docker is built on an open foundation, starting from the drivers layer, which enables the open source baseline kind of software components to leverage the hardware capabilities. Then we have the SDK layer, the libraries, which can enable secure and performance accelerations for the applications. And the highest level is basically services, which are kind of out-of-the-box implementation of the services, which can be consumed as is, and they are leveraging the best performance which is provided by the underlying libraries. So Docker is our complete software framework, which enables all the hardware capabilities across our adapters. And basically, Docker makes it possible to leverage acceleration for all the different kind of workloads, networking, security, storage, AI, and many others. So this is a baseline of our software offering for the networking. Specifically for AI cloud, so it's very important basically that the AI clouds has accelerated infrastructure, because there is incredible need of the data intensive applications in the AI cloud. So they demand high efficiency, high throughput, and basically top performance in order to reach the scalability and sustainability goals. For that, Docker provides actually all the needs and to support these demands and reach the goals of the AI cloud because of this kind of intensive requirements. So specifically what Docker enables for the cloud, and which kind of our partners from Cruise is leveraging, it's a multi-tenant SDN. So Docker can be can enable secure and performant SDN layer, which is needed to isolate the workloads across multiple tenants in the cloud, make them secure, flexible, and basically virtualized networks, virtualized overlay based on our networking adapters. The next one, we have a accelerated virtual switching layer, which is basically backing up the SDN solution running on our DPUs and NICs, and basically to improve the standard virtual switch performance with the ConnectX or BlueField hardware accelerations to make sure that the virtual switch providing the top performance and the lowest latency, which is very important for the AI cloud deployments. And for efficiency, so it's also becoming very critical to maintain the cloud efficiency and basically offloading all the packet processing on the dedicated accelerators on our ConnectX and BlueField devices, on DPU and NIC, just to kind of free up the CPU load and better utilize the CPU and basically make the scaling, effortless scaling possible. And the last one, it needs to be built on the open standard, open foundation. This is basically the base layer of Docker. And for that, specifically for networking, virtual switching, we are leveraging Open vSwitch or OVS and OVN, it's kind of SDN solution for OVS, which basically enable the open source virtual switch backed up by the community support with all the benefits which Docker and our hardware acceleration can provide. So in short, basically Docker acceleration provides a really high performance and energy efficient way to back up the AI cloud deployments and help to basically save power, get to the best performance and reach the sustainability goals. So, and the last part of this, basically of all these networking offerings that we kind of we provide for the AI cloud, this is OVS Docker. So OVS Docker is one of the services which is available as part of the Docker framework, and OVS Docker is a key component of the Docker framework, and basically it's bringing the user space acceleration based on Open vSwitch. So it can act as a drop-in replacement of the standard virtual switch, delivering very high performance and across all the NVIDIA hardware. It can work on BlueField DPUs, on ConnectX NICs and Super NICs, and basically serve as a base layer of the networking acceleration, which is kind of optimized for demanding applications such as AI. So OVS Docker is leveraging Docker libraries to make sure that it can offload the networking functions into the hardware to maximize performance, scale, and also functionality and capabilities, which is really critical for deployments in AI, in the cloud, and in the telco use cases, to make sure that the workloads that are used in these domains, they actually can get the best performances possible. Specifically, that we optimize in OVS Docker is a connection tracking, which is important technology, which is used in the clouds in general, and especially in the AI cloud, basically to enable accelerated cloud gateways with the security, with the security groups, with the overlay NAT, and other features which is typically found in the cloud deployments. So OVS Docker is really, we invest a lot in making this feature is really optimized to deliver the highest bandwidth up to line rate, the packet rate, and also the latency. And on the next kind of part of the presentation, my colleagues will show the real results of this improvement. And the last one, so basically OVS Docker is powering all our networking services, such as HBN, the service for routing. Also, it powers the open source SDN services, which is based on OVN, which Crusoe is using as a base layer of the multi-tenant cloud VPC, and even third-party services. So basically, it's acting as a base component which can deliver the performance and scale to the higher level services. And OVS Docker is designed as basically originally using the open source upstream OVS as a baseline with specific Docker enhancements. And we plan to enable these enhancements to collaborate with the OVS community and bring all the features and all the benefits which Docker delivers as part of OVS Docker to all the OVS users, inbox OVS users in the future. So basically, it's also becoming the open and upstream implementation of the user space virtual switch with all the performance advantages that anyone will be able to leverage in the future. And now I want to hand off the things to Gavin from Crusoe Cloud, and he will be sharing actually how they leverage NVIDIA accelerated technology, specifically OVS Docker, to kind of reach the remarkable performance and also feature capabilities in the cloud, in the real world deployment of the Crusoe AI cloud. Yeah, thanks, Gavin.
So this thing on, yeah, okay. So at Crusoe, we have been partnered with NVIDIA very closely, and number one, thanks to the NVIDIA team for the opportunity to speak on this and the work that we've done together. So been working really, really closely with the NVIDIA team in order to get adoption of the Docker framework into our cloud platform. If you jump to the next maybe couple of slides. Yeah, so we're going to be talking about like how we bring this to life, this technology to actually get the infrastructure that matters to our customers into their hands. Obviously, GPUs are the hottest thing in the world right now, and we want to put these things into the customer's hands. But the GPU is only part of the story. Storage is a massive part of actually the story too. You have to be able to have accelerated networking in order to feed these IO hungry systems. So who are Crusoe? So Crusoe is a vertically aligned, integrated, sustainably powered AI cloud infrastructure company. From the bottom up, we look for environmentally aligned power sources. We have a world-leading digital infrastructure group at Crusoe, and they really, source that power for us, and we then go and obviously use that power to deploy our infrastructure as a service. We build AI data center infrastructure. We have some of the biggest projects on the planet going on right now with that world-leading digital infrastructure group. On top of that, we build our AI cloud platform, and then on top of that, we build managed AI solutions such as like inference and services that we've just launched So we're purpose built for AI. We have enterprise scale infrastructure, and we really do have like world-class support. It's one of the things that make us really stand out is our ability to very, very quickly get on any issues on customers' behalfs. I mean, like this infrastructure is complex and it really needs a lot of attention. And we spend a lot of time, like number one, tuning the system for performance. But there's always outliers, of course. Everybody's had issues with a GPU falling off the bus, just the way it is. You got to get your support team on that pretty quick, and that's one of the things that we really do well. The fact that we're like vertically integrated means that we can actually, get more cost-effective solutions into customers' hands, and as much as possible, we can go use sustainable power sources to power that infrastructure. We have some amazing customers that just do absolutely unbelievable things in our platform. Even we're a customer of our own customer in some sense. Like, I use Codium's AI code assistant. I'm a pretty dangerous coder, so I need as much help as I can get. Just to give you like an actual practical example of like, we brought Crusoe Cloud to life in modular data centers up in North Dakota / Montana border, where we're using flare gas to power the GPUs. And one of the most amazing things about this is like Crusoe has an oil field operations team that are out there in all environments, some of the most horrendous weather conditions you can ever imagine. And they kept that first project that we built together, up and running. But then you obviously have to expand beyond that, right? So we have more traditional data center footprints and then go into sort of like hyperscale. So another example of a project that we did was bringing GPUs to geothermal power in Iceland. And we have a pretty sizable footprint that we have deployed and are continuing to deploy and expand in Iceland right now. So that's the base story, but like what we're here to really talk about is on top of that is accelerated networking. And what is it that we're actually accelerating? Well, Crusoe Cloud is truly multi-tenant. So, we deploy a physical infrastructure, and on top of that, customers can come along and provision their own infrastructure. So it's just like VPC networking that you'd expect in any cloud. And this really simple diagram on the right here is just to show you like the very base components, the simplest mental model that we can use to think about this. So we, as Alex has pointed out, like we were big users of the Oven project. That brings all of the layer 3 features that we need to really bring Open vSwitch to life. At its most simple form, Open vSwitch is just a layer 2 switch, a very, very simple OpenFlow pipeline. But if you want to do some really complex things and you don't want to talk OpenFlow all day, every day, you want a higher level sort of abstraction, and that's Oven. And that provides these primitives such as logical routers, logical switches. It gives us, DNAT and SNAT, load balancing, security through ACLs or ultimately a firewall. And then we basically accelerate that logical pipeline onto the ConnectX SmartNIC. And we're going to talk about the journey that we went on from initially launching Crusoe Cloud to where we're at right now and continuing to accelerate. And like I said in the sort of takeaway there, I was talking about one of the most critical things to make GPUs useful is to be able to feed the GPU with enough data, and that's really to accelerate using like software-defined storage. So data path acceleration. This is a really simple diagram I put together to explode out that compute node that we just talked about. And what I'm exploding out here is just a mental model for the actual logical network path that we're actually implementing. I could have dumped a whole bunch of OpenFlow onto the screen and it wouldn't have meant much. So it's really useful to just use these logical primitives to think through what we're actually accelerating. So in the previous slide, we introduced maybe just a couple of different tenants to use as the mental model. And we can think about the traffic that has to move in VPC networking as being either traffic that moves within the VPC context, so traffic that's moving east and west. That's traffic that will require stateless offload. So whether your encapsulation layer for your VPC networking is Geneve, or if it's VXLAN, you want to offload that encap and decap process. And then obviously a massively important thing is the stateful operations, like delivering connection tracking. So connection tracking can be used for, stateful NAT, which is really important to us. The context there is as you leave the VPC context and you go out to something that's external to the VPC, you of course want to have some sort of NAT in place. You got to get to Google right. So CT for NAT is one thing, and then firewall rules is something else. We want to put it into our customers' hands, the capability to express their own security posture and security rules, and then we want to make sure, of course, that that's fully offloaded. So you can imagine, in the world of this is quite a complex logical pipeline, and if this was all done in software, it would just eat a ton of CPU, and the CPU is obviously capable of moving packets through it, but not at the sort of rates to feed a GPU, especially in modern GPU architectures. So everything is accelerated. So this talk has actually got almost two paths of acceleration. We're trying to obviously dramatically reduce the amount of CPU we have to throw at the system to handle packets and move them at line rate. And this next slide sort of shows this journey that we went on. It was initially using Open vSwitch in kernel mode. And, so if we think about this, there are two paths. There's the slow path and there's the fast path. The fast path, of course, is every packet that's handled on the eSwitch and the NIC and hardware. Super fast, can move packets at line rate. But there is a slow path, right? What is the slow path? The slow path is basically any packets where there's no rule and the eSwitch had to be handled somehow, right? You have to program the eSwitch. So for us, OVS kernel mode it's kind of become a bottleneck because you have potentially a very, very high rate of connections getting turned over in the system. As we move from training to inferencing, customers are of course building super cool applications, and now they want to bring those applications to the world and they want to serve them. So that's where the sort of paradigm shifts. Now we move in from just moving data east-west within our data center or within the VPCs to actually going north-south to be able to actually provide services where customers can connect. And that's where the slow path has kind of become a bottleneck. There's less determinism, and at very high connection rates, you can actually see a bit of CPU utilization. The journey then is kind of taken us away from Open vSwitch in kernel mode towards Open vSwitch in Docker mode. And we're really looking at at very, very high connection rates. The CPU utilization is still well within a reasonable bounds. It's just super efficient. We can move a very, very high connection rate without incurring too much CPU utilization in that exception path, that slow path. And then one of the most important things is really stable deterministic performance. Our customers want to know that under any sort of load conditions that they impose on the system, that is at least deterministic. And the fact that the efficiency comes from the fact that Docker reallocates a CPU to handling those slow path actions. It's super efficient in how it handles that. And we're going to talk about this in this slide. So Again, this is just a mental model of the thing that I was just speaking about, right? There's a couple of different paths or a few different paths that traffic take in the system. Think of anything that's not that blue line as like an exception packet. So it's something that we need to handle. We need to program the hardware somehow. And in kernel mode, that can get super expensive with those high connection rates. What Doka is doing here is basically, you'll see, I hope it's clear, that there's kind of no kernel space involved here as we move to the right side of the diagram. So what it allows for is just at these very, very high connection rates to ultimately have much more determinism. And that's key for us. Like that's given us, the capability to do more and more on these systems. We offer systems, that we can potentially have up to 50 different customers, maybe more, on the same compute node. So that's all cool, but what does it mean in practical terms? And this is where Nipur and I have been working together. So Nipur is going to run us through some of the performance results here. But first of all, we had to come up with a way to validate that the performance that we're looking for, we can actually get that with Doka. So we came up with a test environment in which we basically just build a contrived pipeline that has all of the features that we need at Crusoe to actually deliver these services to customers, and then measure what the performance improvement is when we move from kernel mode into Doka mode. So we did this basically. We went to our friends at Keysight, and they have this really cool piece of software called SciPerf. And SciPerf is just a DBDK-based traffic agent. It's very, very useful in virtualized environments. So we do some like initial setup with SciPerf, and what we can do is like we can make SciPerf like a fully fledged traffic generator that can use the CX7 card, can use the virtual machine to actually emulate the worst case scenarios that we could ever throw at the system. This means that we can run this thing up to 400 gigabits per second bidirectional. We can put hundreds of thousands of connections per second through the system. When I say hundreds of thousands, imagine that you're not using CT and you're just moving east-west in the same VPC context. What you're going to see is like you don't have to invoke connection tracking. So the system can handle a lot of connections, and it's all stateful. That's really useful for us. But for testing that north-south, that's where the really expensive operations happen, CTNet and firewall rules, etc. So being able to test that at the worst possible scenario for the NVIDIA team has been awesome for me, because I get to work with them every day to improve that performance. And this is where Nipur comes in, that we work on pretty much dialing on Doka performance. So
thanks, Gavin, for explaining the test setup in detail. Before discussing the numbers, I want to highlight that the pipeline created here in Oven is specifically designed to exercise the connection tracking enabled for NAT, because that's the most basic and common requirement we see with customers like Crusoe. So as part of the Crusoe's journey to evaluate whether OVS Doka is the right fit for their AI cloud needs, we started with checking baseline performance and ran a series of tests to see where we feel the need for acceleration is. So here we are comparing OVS kernel with hardware acceleration enabled to OVS Doka. The first test we ran here is the throughput test with a 400 Gbps bidirectional throughput of 20 MB payload with stateful NAT enabled. And we use SciPerf to simulate real-world traffic, in the sense that the test application will open a connection, send 20 MB of data using the HTTP post and GET request, and close the connection, just like how it happens in real world. So we have this special setting called max transaction equals 1. So we see that both OVS Doka and kernel are able to reach the line rate of almost 400 Gbps. Here, green line is with Doka and the blue line is with kernel. Now, the way SciPerf works is it tries to ramp up the number of connections per second to achieve the set objective. So here we see that with around 1200 connections per second, we are seeing the line rate performance. So this is still our favorable case because roughly we are sending around 2200 packets since the MTU is set to 9K, right? But remember that indicating that OVS kernel and Doka perform similar at smaller CPS. But there is a catch here. So here CyPerf is continuously opening the new connections and deleting the old ones, right? So there will definitely be a software activity because in both the modes, only the packets in the established state are offloaded to the hardware, whereas the opening sequence and the closing sequence packets are still processed in software. So let's see what the CPU utilization looks like for both. So here in OVS kernel, needed 5 cores to be able to sustain the line rate at 1.2K CPS, where it's a combined activity of kernel space, mainly the K-worker threads using the NetFilter module to offload the request to the hardware, and the user space, which is the handler and leave validated threads doing the upkeep work and the slow path packets. In comparison, OVS Doka only needed 1 core to do all of that. So you'll be saving 4 cores when going with Doka mode. Now let's try to focus on where do we see the need for acceleration. The second test we ran focused on the scale. So we compared both the modes at 25,000 connections per second at 450 KB payload. This rest of the settings are same. The max transaction is set to 1 and stateful NAT is enabled. So this is a short-lived connection compared to the previous one. Here we are sending around 50 packets since the MTU is set to 9K. Now, here we see that both OVS Doka and kernel are able to reach the line rate of 25K CPS, but Doka is still faster in reaching that rate, high rate, and is stable throughout the duration of the test. Now, compare that to the previous test. So in previous tests, the CyPerf application was recycling the connections at around 1.2K CPS, right? Here, that's happening at a much higher rate, 25K CPS. And especially in the kernel mode, since you have to context switch between the kernel space and the user space, and there will be an interrupt handling for all the slow path and exception packets going up to the software, there will definitely be a latency and high CPU utilization. So we analyzed those numbers as well. Let's see what those looks like. Looking at the average connection latency profile, OVS Doka is around 175 to 200 microseconds, whereas kernel is around 400 to 500 microseconds. So you will still get a lower latency profile with Doka. Now, you will say that, okay, it's not that bad with kernel, but let's see what cost was to reach this performance. Kernel mode needed 30 cores to sustain the traffic of 25K CPS, whereas Doka mode, it was just approximately 2 cores to do all of that. So here you will start seeing the benefits of acceleration with the scale. Now let's push the stakes even further, right? We increase the CPS to 50,000. And the rest, all parameters are same for 50 KB payload and stateful NAT enabled. Here is where you'll see the need for acceleration and not just the benefit of the acceleration. So OVS kernel needed almost 5 minutes to reach that high CPS rate and stabilize, whereas Doka reached that high rate in seconds and is stable throughout the duration of the test. Similar to the previous test, we analyzed the latency profile and CPU utilization in this case as well. Here, OVS Doka offers stable latency of around 1 millisecond throughout the test, right? And with OVS kernel, the latency is not just higher, it's non-deterministic, ranging from 1 millisecond to 18 milliseconds. So to be able to run at that scale, you definitely need acceleration with Doka to have whatever Crusoe's requirements, which Gavin listed just now. And look at that CPU utilization, it's through the roof. Kernel mode needed 86 cores to sustain the traffic of 50K CPS, whereas Doka, it's consistently 2 cores. Now, to summarize, right, here you will see that at smaller CPS, both kernel and Doka perform similarly with some utilization, CPU utilization in kernel mode. But as you scale further, you start seeing the need for acceleration with Doka. Kernel mode, even utilizing high amount of resources, is not reliable and deterministic, whereas Doka offers excellent performance and the main important factors responsible for helping us achieve that excellent performance is it's totally a user space solution. So you don't have any overhead of context switching between the user space and the kernel space. We have a PMD thread continuously polling for slow path exception packets, so there is no overhead of interrupt handling. And the third and the most important factor is using Dokaflow API, which invokes hardware steering. Hardware steering is different in the way that it has dedicated hardware resources to define the logical pipeline in the hardware and is designed to be performant at scale of around 1 million connection insertion rate. These are the factors related to the megaflow offloads in the Open vSwitch. But when it comes to the connection tracking, we do a different architecture for defining the CT offloads in the hardware and a synchronous model compared to the asynchronous kernel model, which really helps us in achieving the best performance. To conclude, OVS Doka offers better performance, be it throughput or connections per second rate, with minimal CPU utilization, and you will get a low and deterministic latency profile for all your workloads. Now, the guiding principle of Doka has been that we do what's necessary to harness the full potential of our hardware, and we know that our hardware, be it SmartNIC or DPU, is capable of much more. So this is just the beginning, and more innovations are yet to come. With that note, I hand it off to Gavin to talk about what's coming with 3.0. Thanks.
So we'll wrap up. Just quickly kind of peek a little bit in the future and talk about what's coming next really soon. So first of all, we are releasing Doka 3.0, even more focused on accelerating and securing AI workloads, specifically improving performance of VPC networking with OVS Doka and better OVN integration, and also offloading, accelerating storage I/O with Doka Snap services. And for security, we are announcing the Doka App Shield service, which can integrate both OVS and Snap, and basically secure and mitigate the threat running on the host. And the last one from Doka, we are heavily investing in the new orchestration services to provision and orchestrate DPU services. One of them is DMS, which can simplify management of individual DPUs and NICs. And another one is a Doka platform framework of DPF, which can do the cluster-wide orchestration for DPUs and services. And Gavin, next for Crusoe.
Yeah, so Crusoe, the next, this one on, see if it's, yeah, all right, that one's good. So what's next for Crusoe? So, obviously Blackwell is going to be really important to us to get launched, and, that will be with the NVIDIA Bluefield 3. A huge part of this is like the advanced telemetry and monitoring for OVS Doka, the insights that you get into what is an opaque box today. So you run OVS in kernel mode, it's somewhat opaque as like what's going on. Like you need to dig around a lot when performance isn't exactly where it needs to be. But with the Doka telemetry, we get a lot deeper insights into the performance of the system in real time. There's a lot better metrics that are coming with it. Storage and security, these are obviously really hot topics. Security, like I mentioned earlier, as you move to different workloads, moving away, obviously training will still be a thing, but more inferencing. We want customers to have deeper sort of assurance of security as they expose services to the public internet. And of course, like Alex just mentioned, the DPU management and orchestration is really critically important when we're trying to scale this infrastructure out.
All right, this one's on. Okay, unfortunately, we're out of time, but I want to thank you guys, Alex, Gavin, for a fantastic presentation. Since we don't have time for the Q&A right now, I'm going to ask you, the panelists might be willing to spend some time in the hall to answer any questions you might have as we get ready for our next session. But that concludes this session for today, and I want to thank you all for being here. Appreciate it.